Welcome back, everyone. Now that we understand how image kernels and filters work, let's go ahead and see how they play a role in the convolutional layer portion of a convolutional neural network. Recall that running an artificial neural network that was just a fully connected feed-forward neural network for the MNIST dataset actually resulted in a network with relatively good accuracy. However, there are some issues with always using ANN models for image data. So if we were to always use artificial neural networks, just normal fully connected networks for image data, we would end up with a huge amount of parameters. Recall that when we actually checked the parameter count for our network on the MNIST dataset, we had over 100,000 parameters, and that was for tiny 28 by 28 images. 28 by 28 pixel images are really small compared to your images that you're used to in normal life. For example, you know that your resolution on just a normal monitor screen is probably like 1080p. That's 1080 pixels or 1080 pixels. That's a lot larger than 28 by 28. So if we try to scale an artificial neural network to just normal sized images, you're going to end up with not just 100,000 parameters, but a million parameters. And so training time is going to take forever. The other problem with an artificial neural network is recall that we had to flatten out the data before actually feeding it into the network. And if we flatten out the data, we basically lose all two-dimensional information. And the other issue is an ANN will actually only perform well where images are extremely similar. And if you take a closer look at the MNIST dataset, you'll notice that essentially all the numbers are centered in the image. We want our convolutional neural networks, or just our networks in general, to be able to recognize a number regardless of where it is in the image. An artificial neural network will actually not be able to do that. If you were to take a 28 by 28 image of a handwritten digit, but the digit was not centered, maybe it was starting all the way on the right, and feed it into that artificial neural network we trained, you would actually not get good results. And it's most likely that the network would not be able to understand what it was actually looking at. So the MNIST dataset is really special because all the numbers are perfectly centered in these really small 28 by 28 images. And that's why the artificial neural network was actually able to perform so well there. But later on we'll see that this network won't generalize well to just normal sized images, especially when what we're looking for could be anywhere in the image. So we have a lot of restrictions for the artificial neural network. Now a CNN, or convolutional neural network, can use what's known as a convolutional layer to help alleviate a lot of these issues. A convolutional layer is created when we apply multiple image filters to the input images. The layer will then be trained to figure out the best filter weight values. A CNN also helps reduce parameters by focusing on local connectivity, and we'll actually see an example of this localized connections. So in a convolutional neural network, specifically in this convolutional layer, not all neurons will be fully connected. Instead, neurons are only connected to a subset of local neurons in the next layer, and these actually end up becoming the filters. So let's understand this local connectivity and its connection to filters by beginning with a very simplified one-dimensional example. And then later on, we'll expand this to two-dimensional inputs for a grayscale image, and then later on to a three-dimensional tensor input for a color image. So here we have just a normal artificial neural network. We see here on the left-hand side we have some sort of input, and then it's fully connected to all the neurons in the next layer, and then that would continue on throughout the network. So because this is fully connected, there are lots of parameters, which we've already decided is going to be a problem for really large images, or even just normal-sized images, because of training time to figure out all those parameters. So how do we reduce these number of parameters? Well, a convolutional layer, what it does is it focuses on local connections. Notice now that the neurons are only connected to a local neuron in the next layer. They're not connected to every other single neuron. So here we have these localized connections, and this is just being shown on one dimension. Later on, we'll expand this to two dimensions. But we can see here that we actually have one filter. So what's going to happen is because of this essentially convolutional layer with a localized connection, these localized connections end up creating this filter. And the network itself is going to figure out what are the best weights for this filter. And so what we could do is then maybe add another filter. And as you're training your convolutional neural network, you actually get to decide how many filters you want to apply to this image, and essentially have the network learn the best weights for the filter. So previously we saw that really common filters, such as a blur filter or an edge filter, those weights are already known. But if you're working with maybe facial recognition data and you're trying to figure out, well, what filter values are going to be really good at recognizing eyebrows, you yourself are probably not going to be able to figure out those numbers. But the convolutional neural network will somewhere along the line probably be able to figure out some filter which is good at recognizing some component of that face. Keep in mind, it's going to be difficult to actually open up, so to speak, the neural network and decide what each filter is actually looking at on those face images. But it's likely that the filters will begin to recognize higher and higher patterns related to a face, like eyebrows, noses, ears, mouths, etc. And we'll talk about interpreting the filters of a network and visualizing that later on in the course. But here we can get an idea that through these localized connections in this convolutional neural network, we can then have kind of a stacked number of filters. So that was a simple one-dimensional example of convolution. But recall, these grayscale images, those are two-dimensional. And we mentioned that we wanted to preserve the two-dimensional relational information in the convolutional layer. And this is where our knowledge of those image filters or image kernels comes into play. So let's expand this now to 2 dimensions. And it's actually quite simple. Here we have an input image. It's a really simple image. It's just 3 by 4 pixels. And recall that since this is a grayscale image, essentially each value falls somewhere between 0 and 1, or depending how it's normalized, between -1 and 1, or 0 and 255 is another really common pixel value. But the main idea here is these are pixels, and they're technically just numbers or a matrix we're feeding in here. So here's our input image, kind of just this really simple Y shape that we're showing here with darker zeros and lighter ones. Then what we're going to do with this input image is recall that we have this filter that we can essentially scan across the image. And other things to remember is that if we wanted to, we could pad the image, and we can also choose a stride length. So what we're going to do is here in 2 dimensions, we're going to focus on localized connections using this filter process. And recall again that we can edit our stride size. And so eventually what we end up doing here is we get these localized connections from these input images or input features of these pixel values and connect them to only certain subsets of neurons in this next layer. And you'll notice that essentially what we're creating here is a filter. And then it's up to the network to figure out what weights it should be applying to this filter during training to correctly classify the images. And if you want, you can always do this with another set of filters. You can add on as many filters as you want here. So you do the same scanning process again and again, and here we have 3 filters on this input image. But it's not uncommon to see tens or hundreds of filters depending on the complexity of what you're actually trying to classify, as well as how many different types of objects you're trying to classify. So if we were kind of to stack these filters together, that's what begins creating our convolutional layer. It's essentially this stack of filters for the convolutional network to figure out the proper weights, and each of these filters only has localized connections because we understand how the image kernel is convolved across that image. Now keep in mind, that was an example for technically just a grayscale image, but what about color images? Color images can be thought as 3-dimensional tensors consisting of red, green, and blue color channels. Additive color mixing allows us to represent a wide variety of colors by simply combining different amounts of red, green, and blue. So you've probably already heard of RGB color coding, red, green, blue color coding. And the idea behind that is, through some combination of red, green, and blue, you can create any version of any color. Now keep in mind, there are limits to this. Our RGB can't produce every single color available, but it does produce a wide variety of colors that we can see on a human scale. So you're not going to be able to see things like ultraviolet or infrared, but RGB does allow you to create what's known here as this range of colors. Now each color channel will have intensity values, and you've probably already seen this if you've ever worked with representation of color pixels and other software of RGB sliders. So here we have RGB sliders, and essentially we choose some value between 0 and 255 for red, green, and blue, and you essentially mix them together as if they were paints, and you get some sort of color out. The main idea being is that these colors can essentially be represented as a mix between red, green, and blue. So what does that mean for our actual images? So here we can see an example of breaking down a full color image into its color channels. So for a single color image, we have these actual 3 dimensions. We have the height and the width, something we're already familiar with, but then for every single color channel, that is one for red, one for green, and one for blue, we're actually going to have a separate array of pixels. So this means when you actually read in an image and check its shape, it's going to look something like this. You'll have maybe 1280 by 720 by 3. So that means that this single image has 1280 pixel width, 720 pixel height, and then 3 color channels. And keep in mind that each of these color channels is essentially, if you were just to grab one of them, it looks like a grayscale image. It's just values between 0 and 1, or 0, 255, or -1 and 1. They just represent the intensity for that particular color. So we can see here the intensity for red, green, and blue. And then when you combine those intensities, as we previously discussed here, you end up creating mixes of colors, which produces this color image. So again, we think of this as the height, the width, and then 3 color channels. And recall, this is just for a single image. So now a single image is actually this 3-dimensional tensor. You should also keep in mind that the computer won't actually know if a channel is red. It just knows that there are now 3 intensity channels. So you should also keep that in mind in case your images happen to have different color encoding. Certain programs will actually encode, instead of red, green, blue, they'll encode it as blue, green, red. That won't really matter that much for our use case of the convolutional neural networks because the network doesn't really care what order the colors are being fed in. It just cares that there's 3 intensity channels. Now, the question arises, we just saw how to perform a convolution on a 1-dimensional array, then we saw how to perform it on a 2-dimensional array. How do we perform a convolution on this color image since it's a 3-dimensional tensor? So what we actually end up with is a 3-dimensional filter with values for each color channel. So essentially, this filter now has 3 dimensions to it. We have the actual height and width of that filter shown as 3 by 3, but then we have an instance for each dimension for the color channels. So there's one for the red, one for the green, and one for the blue. And just as before, we can have as many filters as we want. So we can create another filter. And again, this filter is 3-dimensional. It has one little image kernel per color channel. So one for red, one for green, and one for blue. And we can keep adding on these filters. So you should now be thinking of these filters for these color images as 3-dimensional. And later on in the course, we'll actually expand from grayscale images and we'll move on to color images so we can get an idea of working with this extra dimension of data. Now often, convolutional layers are fed into another convolutional layer. So it's not uncommon to see a convolutional layer being directly stacked and fed into another convolutional layer and then stacked and fed into another convolutional layer. And what's really cool about this is this allows a network to discover patterns within patterns, usually with more complexity for later convolutional layers. Now we've learned a lot so far, and we have one final theory topic to cover before coding our own convolutional neural networks, and that is the pooling layer, also known as the downsampling or subsampling layer. Once we understand how the pooling layer works along with the convolutional layer, then we have all the pieces we need to actually create our own convolutional neural network, and then we'll revisit that MNIST dataset problem. So in the next lecture, let's go ahead and discuss pooling layers. I'll see you there.